We're at Group 21, and our project focuses on creating a stretched biosensor for cardiomyocytes.
Hi Saul, how are you doing today? What brings you in?
Hello, doctor. So I came in today because I haven't felt very well in the last few days. I've been experiencing shortness of breath, a lot of chest pain, especially when I do my morning runs. And I broke up with my girlfriend, so I was wondering if maybe that has anything to do with it.
Wow, that sounds awful. We'll do some examinations and tests to see what the problem is. Hi Saul.
Hi, doctor. So what did the results say?
I'm sorry to be a bearer of bad news, but you've been diagnosed with hypertrophic cardiomyopathy. Your heart muscle is thickened, adding a stress load that's making it more difficult for your heart to pump blood. This explains the symptoms you've been feeling.
Wait, so am I going to be okay? Is there a cure for this?
Unfortunately, in your case, the most viable solution requires a heart transplant surgery. However, donor organs are limited and the process may be very invasive and costly.
Heart transplant? That means a huge scar? Is there a better solution?
Oh, unfortunately not.
Cardiac hypertrophy is an adaptive increase in heart mass in response to hemodynamic pressure. It progresses pathologically when excessive stress leads to fibrosis, mechanical stiffness, and cardiomyopathy. Sudden death occurs in a small number of patients with hypertrophic cardiomyopathy. Heart disease therapies are often expensive and invasive, thus minimizing the risks and cost of current and developing treatments is of utmost importance.
The goal of our research is to enable accurate monitoring of microRNA expression levels in cells experiencing cardiac hypertrophy after 24 hours of stretching. Our solution is to create a set of mRNA biosensors that, when transfected into cells, fluorescently detect for mechanical and norepinephrine-induced stretch in cardiomyocytes.
Now we will present some animations to show how our sensor works. When our sensor is transfected into a cell and no target microRNA species are present, the ribosome will translate the sequence of the sensor to green fluorescent protein, or GFP. When target microRNA molecules are present, they will bind to complementary sites on the sensor and physically block the ribosome from translating the GFP gene. The significance of our biosensor is that it will be able to fluorescently detect whether or not the microRNAs related to pathological stretch are presented in the body. To give a better representation of our design, here's a live reenactment of how our biosensor works. In the absence of target microRNA, the sensor will produce GFP. But in the presence of target microRNA, the complementary site on the sensor will be bound to the free-floating microRNA, thereby inhibiting fluorescence.
This sensor will eventually be used in high-throughput screening assays to discover inhibitory drugs for cardiac hypertrophy. Through the development of this biosensor, we hope to save many lives affected by cardiac disease with developing medicines as a non-invasive solution to this problem. In this way, people can continue to enjoy living longer lives and healthier lives.